All right, in this example, we're given a voltage function in the form of this graph, and this voltage is across a 100 microfarad capacitor. So this is 100 times 10 to the negative 6 farads. We want to use this and graph the current, power, and energy. So the first thing we could do is, using this graph, come up with a piecewise defined function for the voltage. So in the beginning, over here in this area, right before, when t is less than 0, the voltage is 0. And then from between 0 and 10 to the negative 2, it's this linear function. And that slope, let's see, rise over run. So we've got 0, 0, and then 10 to the negative 2, and 100. So that rise over run is 100 divided by 10 to the negative 2. That's actually going to be 10 to the 4th, or 10,000. And so this part is just a line of slope 10,000 going through the origin. So that's 10,000 t. And that's between 0 and 10 to the negative 2. And then at which point it reaches 100 volts and stays steady there. So it's 100 for t greater than or equal to 10 to the negative 2. Here our time units are in seconds, our voltage units are in volts. And we're going to find current, power, and energy. So let's start with current. The current is given by capacitance times dV dt. And so we're going to use our voltage function, and we're going to find a different function for each of these 3 time intervals. So I'm just going to take whatever the voltage is and multiply it by the capacitance, or sorry, the derivative of the voltage and multiply it by the capacitance. So our capacitance is 100 times 10 to the negative 6 times the derivative of the 0 function is 0. For between 0 and 10 to the negative 2, we have 100 times 10 to the negative 6 times, and then the derivative of 10,000 t is 10,000. And then 100 times 10 to the negative 6, our capacitance times the derivative of the constant 100 is again 0. So simplifying these, we have a capacitance, a current of 0 for t less than 0. We have a current of, let's see, this is 10 to the 4th. So, when we multiply these, we'll get a current of 1 between 0 and 10 to the negative 2. And then a current of 0 at the end for values greater than 10 to the negative 2. And these are in amps. We could graph this. So let's see, it starts out at 0 for t less than 0. Between 0 and 10 to the negative 2, our current is 1. and then it drops down to 0 again. So now we have, we were given voltage, we found current, we also want to find power. And knowing voltage and current, finding power, we can do that by just taking the equation P is equal to V times I, current times, or voltage times current. And so if we multiply these together, right, for each interval, right, the current is 0 at the two end intervals, right, for t less than 0 and t greater than 10 to the negative 2. And in between it's just 1, so that means that our power is going to be 0 at each of these two, the beginning and at the end intervals, and then in the middle, from between 0 and 10 to the negative 2, it's just going to be equal to whatever the voltage function is, because we're multiplying it by 1. And so that becomes zero for t less than 0, 10,000 t between 0 and 10 to the negative 2, and then 0 for t greater than or equal to 10 to the negative 2. This is fairly simple to graph. Hours in watts. So at 10 to the negative 2, if we plug this in for t, at 10 to the negative 2, it is up here at 100. So it's 0 before, then it's this linear function, then it drops down to 0. All right, so we've got our current and power. The last thing we want to find here is energy. To find energy, we can use the relationship that energy is equal to the integral from minus infinity to t of the power function d tau. We kind of use this as a dummy variable. This is this improper definite integral. And when we evaluate it from minus infinity to t, we will get a function of time. So let's consider these different intervals. So for t less than 0. All right, so let's remember that power we've got these three functions, or these three pieces of the power function. So for t less than 0, energy is the integral from minus infinity to 0 of the 0 function d tau. And this is going to give, when we think of this as this definite integral as area under a curve, if we go back and look at this, the area under, from the total area under this curve from negative infinity to 0 is 0. It would normally just be, some constant. When we integrate it as a function, we just get some constant. But we know that this is going to be 0, and that's basically our initial condition. So, knowing that the energy is the integral from minus infinity to t, as a function of time, we've got it from minus infinity to 0. Now we're going to look at the next part of the interval from 0 to 10 to the negative 2. And the way we're going to get a function that's valid on this interval, it's still the total integral starting at negative infinity. So what we're going to do is take the integral from minus infinity to 0, plus the integral from 0 to t. These two integrals together give us the integral from minus infinity up to t, which is what we want to get a function that's valid on this interval. Now this first integral we know is 0. And this next one, we're going to integrate from 0 to t. That function on this interval is 10,000 as a function of tau now. I'm just putting in this dummy variable, 10,000 tau d tau. We'll sort of see how this will still give us a function of t in the end. When we integrate 10,000 tau d tau, it's just the power rule. We get 5,000 tau squared from 0 to t. And of course, I'm going to just ignore the 0 now. And this is 5,000, and now I'm plugging in t for tau, so t squared minus 5,000 times 0 squared, and this gives us 5,000 t squared. So we do in fact get a function of t when we're finding energy. And for t greater than 10 to the negative 2, our energy is the integral from minus infinity to 0 plus the integral from 0 to 10 to the negative 2 plus the integral from 10 to the negative 2 up to t. So this first one we know is 0. This second one, we've already done the integration, so this is 5,000 tau squared from 0 to 10 to the negative 2 plus, and again now from 10 to the negative 2 to t, if we look at our graph, thinking of this definite integral as a function, as given the area under the curve. The area under the curve in this region is 0. So this also gives us 0. So now we can evaluate this expression. So when we plug in 0, that'll 0 out. And when we plug in 10 to the negative 2, we get 0.5 joules. So our energy as a piecewise defined function is 0, then 5,000 t squared, and 0.5 on our intervals. So it's this quadratic in between 0 to 10 to the negative 2, so it kind of looks parabolic, then it holds steady. Of course, it's 0 to begin with. In this next example, we're given a current function in the form of this graph, and we want to find and graph the voltage. Again, this is a current through, we're working with a 100 microfarad capacitor, so that's 100 times 10 to the negative 6 farads, or 10 to the negative 4 for our value of C. And we'll start by writing out this function as a piecewise defined function. So it starts out 0, then we have a couple of linear sections in the middle, and then it ends at 0. So we're going to have 4 regions here. 0, t less than 0. Then from 0 to 10 to the negative 2, we've got a linear function that goes to the origin, so it's just a constant times t, and the rise over run is 1 over 10 to the negative 2, so that's 10 squared or 100. So this is 100t. And then between 10 to the negative 2 and 2 times 10 to the negative 2, we have another linear piece. It doesn't go through the origin this time, but you could find it's got the same slope, just negative, because the rise over run is just it's just downward at the same magnitude. And you can use algebra to find the y-intercept, basically just using these 2 points. And if you do that, you'll find that we have a line of negative 100t plus 2. And then it's 0 again. For t greater than 2 times 10 to the negative 2. Okay, so we're going to find the voltage, and the voltage is given by, if we know current, 1 over the capacitance times the integral from minus infinity to t of I d tau, and we're just going to consider the time regions, right? These different intervals like we did in the last example. So for t less than 0, is the integral from negative infinity to 0 of the current. The current is 0, and if we think of this as area under a curve, this gives us 0. And that's basically our initial condition. On the next interval, we're going to integrate from minus infinity to 0. Oh, I forgot the 1 over c. It didn't matter before, but I want to make sure I include it here. Of current plus, let's see, this would be the integral from 0 to t, 100 tau d tau. This first part is 0. And 1 over c times, if we integrate this, we get 50 tau squared. The capacitance is 10 to the negative 4th. And if we plug in our limits, we get 50 t squared minus 0. So we have let's see, that would be 500,000 t squared, or 5 times 10 to the 5th t squared volts. So that's valid on the interval from 0 up to 10 to the negative 2. Our next interval again, it's cumulative, so I'm going to take the integral from minus infinity to 0. Now the integral from 0 up to 10 to the negative 2. So I'm going to grab all of that voltage. And then the integral from 10 to the negative 2 up to t. The first part we know is 0. For the second part, all we're going to do is evaluate the function we found up here at t equals 10 to the negative 2. So that's 5 times 10 to the 5th times 10 to the minus 2 squared. And then for this next part, we're going to integrate, so we have 1 over 10 to the negative 4th times, integrating this, we get negative 50 tau squared plus 2 tau from 10 to the negative 2 up to t. If we evaluate this part here, that gives us 50. And now we'll plug in our limits here. And we're going to do some distributing and to simplify a bit. So first, I'm just going to try to simplify a little bit here. I'm going to distribute this negative at the same time I'm evaluating each of these. So this gives us a positive 50 times 10 to the negative 4. And this will end up being a minus 2 times 10 to the negative 2. And now I'm going to take this and distribute it through. So we have a negative (5 times 10 to the 5th) t squared plus 2 times 10 to the 4th t plus, let's see, that'll be plus 50. Get those factors of 10 to the negative 4th to cancel. And then minus 2 times 10 squared. And we just have some like terms. So the 50 and 50 is 100, minus 200 is negative 100. So minus 5 times 10 to the 5th t squared plus 2 times 10 to the 4th t minus 100 volts. And that is the function valid between 10 to the negative 2 and 2 times 10 to the negative 2. And we'll note that if we plug in 2 times 10 to the negative 2 at the end of this, if you plug that in, you'll get a voltage of 100 volts. And then looking at the curve up here, looking at the current, we're not adding any more, right? So if we keep integrating, right, and grab the total area under the curve, we're not adding any more area here because that current is 0 for the rest of the time. So we can use this to graph, and you might find it helpful to throw it in a calculator, but for convenience. But we start out at a 0 voltage. Then between 0 and 10 to the negative 2, it's this quadratic function, so it'll be parabolic, concave up, parabolic. And then from there, it's still parabolic, only concave down, right? Because it's a negative t squared. And if you use the calculator to kind of help you graph these, essentially I'm just going to kind of eyeball it. We have 10 to the negative 2 and 2 times 10 to the negative 2. It starts out at 0. If we plug in 10 to the negative 2, you get a voltage of 50. And we already know you get a voltage of 100 up here. So this looks like parabolic concave up on this part, and parabolic concave down for this part.